Okay, thank you, and thank you, Ronny and Ferdinand, for the invitation.
Okay.
Okay, so I'm going to talk about work that has been done mainly at Aalto University in Finland, and this is mainly experimental work, and I show here the people who have mainly been contributing to this, mainly to the experimental part, and my outline here is that I first try to tell you a little bit about heat management on the nanoscale circuits that we are looking at. So my topic really is about thermodynamics in electrical circuits. I start from classical circuits, essentially, where we can verify and make use of the fluctuation relations working with single electrons. So this part really is classical, and it represents the work that we have been doing for the past 5 years. The second part is really going into quantum thermodynamics, in a sense that on one hand, we try to realize quantum heat engines and refrigerators, which really exploit the coherent and say off-diagonal properties of the systems, and also we try to do stochastic thermodynamics using single microwave photon detection, which is still in progress. Okay, this is it. So in the first part, let me tell you a little bit about what is work and heat in this circuit. So in our case, what we are doing is that in this classical part, we mainly look at heat that is transported by electrons that are transferred, say, across a barrier or in general in the conductors. And the simplest example is that you have a tunnel barrier, which is usually formed between two different conductors as an oxide layer by standard techniques. So when a carrier is transported through such a barrier, it leaves behind an excitation, and also it creates an excitation in the target electrode. And if you then just simply add up the two energies that are created in this process, you find out that the energy that you dissipate is always equal to the chemical potential difference across this barrier. So this in these circuits is usually distributed among all the electrons. They form a new Fermi distributed electron system, and then this energy is further distributed as heat to the phonons via electron phonon scattering. So you can under the condition that you can describe these two conductors having a temperature T, you can say that there's an entropy production which is related to this amount of energy that is dissipated. And if you then drive a constant average current through this kind of a barrier, you find out that the average power is always equal to the current times voltage. But of course, in these small systems, we are more interested in the fluctuations, and these are naturally, they are governed by the very well-known fluctuation relations, where the probability of having either positive or negative entropy change over a given time is given by this exponent of the entropy itself. So this is something that one can do in repeated experiments. You monitor the system over time tau, and you find out how much entropy is created in this process. And of course, there is a corollary of this, which is a simple exponent of the entropy, which averages in many experiments to 1. So these were studied in electrical circuits initially under the steady state conditions. You have a system where you have a source electrode and you have a drain electrode, and then you had a double quantum dot in between. So although it's called quantum dot, this is, as I said, pretty classical in the sense that you can consider the electrons as just classical particles that are then quantum tunneled through barriers here. So, so what you can do is you can monitor the position of this particle when there's a chemical potential difference across this kind of a system. You can do it by what is called a quantum point contact, which is asymmetrically coupled to the system. So you can say if there's electron here, or there are no electrons in the system. And this is how it is represented in real time. So you monitor in time the conductance of this quantum point contact, and that tells if the electron is on the left, right, or if there are no electrons. So looking at this kind of a time trace, you can then reconstruct the history of how the electrons have passed, and you find then that because the entropy production or the entropy in this case is related to, as I showed in the first slide, it's related to how much electrons are transported through a barrier. It's given by this net number of electrons that have passed through times the chemical potential difference here. So one can test this, and in these first experiments it was found that it's satisfied to some extent. I mean, not to some extent. It was satisfied to within maybe 20 or 30% under the conditions of chemical potential difference across under non-equilibrium conditions. So, but then what is interesting is, of course, what are the time-driven systems? How are they behaving? So the simplest case is that you have again you have a two-level system. It can be classical or quantum two-level system. You start, for example, in the situation where the particle is on the left well. Then you change the landscape so that the particle starts to make transitions between the two wells, and eventually it perhaps ends up being in the other well. So here we have this is the special case of the general fluctuation relations, which are governed by the fluctuation relations for not only for two-level systems but in general. So in these cases, under the driven conditions, if you start in equilibrium, what you find out is the famous Jarzynski equality, which tells that the exponent of this work divided by temperature averages to unity, and this gives you a possibility to measure, for example, equilibrium free energy changes. And of course, there is also a more another fluctuation relation which leads to Jarzynski called the Crookes relation, Crookes-Tasaki relation, where you have again the probabilities of work in this case in forward and backward processes. So what we can do in these circuits is we can drive them. We can drive them by applying time-dependent gate voltages. Here is our circuit, very simple circuit, which has one tunnel barrier in between here, in the middle here, and then it separates a container to electrons sitting either on the left or right side, and it's capacitively coupled to the outside world, so that the total number of electrons is constant in this circuit. The actual realization is shown here. So now when one puts a voltage here, what is called gate voltage, then the electron is either preferably sitting on the left side or on the right side, and this can be monitored by putting a detector similar to the first experiment, but in our case we use a single electron transistor to monitor the position of the electron. So in each transition, because this system in fact has a very simple electrostatic Hamiltonian, which tells that the energy for each charge state, say there's a charge number n on the right electrode, the energies of these are parabola, like a capacitive charging energies here. So there's a parabola for neutral island on the right, there's a parabola for one extra electron on the right, and so on and so forth when increasing the gate voltage here. So now when one changes this gate voltage, at a certain point you come close to the degeneracy, and the electron can jump between the two dots here, and then the energy that is released to the bath in this case is just given by the instantaneous chemical potential difference between the two islands. And so what one can do is one can register the value of the gate when the transition occurs, and this gives you directly how much heat you dissipate in this process. And now you can count all these elementary processes and find what is the total heat dissipated in this process. And the work, in fact, is then obtained easily by adding the electrostatic energy that you have in the system in comparison to the initial state. So this is all very elementary, but it can be tested experimentally in a very straightforward way. So we have a single electron transistor which is looking at the number of electrons on the right dot here, and then one can put a gate drive here to this gate here, which moves the gate between these two minima, so to say. And then the electron is transported between the left and right dot almost synchronously, as you see. But as you also see, there are many jumps usually if you don't drive the system too fast, and there is some stochasticity in the position of this, of course, in these transitions. So what is the task then? Is just to construct. Since you have registered the gate position where the transition occurs, you have a handle to really evaluate how much heat is produced in this process. And you can create histograms where you measure this dissipated work or heat in this in each of such a realization, which is each experiment is a half of this period here, and you see that at low rates of operation you have almost Gaussian distribution of work, and then when you drive the system faster it becomes less and less Gaussian, and also the average heat is increasing. And for example, you can test the Jarzynski equality, which in this case is valid within about within a few percent. And
when you say set, is that fixing the voltage?
No, SCT is single electron transistor. It is just a single electron transistor. There's another single electron circuit up there which is monitoring, whose conductance is governed by the Coulomb interaction between this dot and the detector itself. So it's simply a detector there, which has some back action, by the way. So it also influences things, but I will not go into that here. Okay, so this is kind of a sanity check. You can do very large statistics. You can take millions of repetitions, and you can get very, very nice histograms. But this is just checking some by now well-known fluctuation relations. But what is of course interesting is if you can do something like a Maxwell's demon, if you can do some information-powered cooling, for example. And the simplest example which we can realize in these circuits is so-called Szilard's engine, where most of you know the idea. So you have a single particle which is in a container, and then you partition it into two with a wall, and then there is an information exchange. So there's somebody who is watching whether the particle is on the right or on the left, and depending on the outcome of this measurement, there is a weight connected to this wall, so that the particle has to push the wall back to the end, at the same time lifting the weight. So in this process, which crucially depends now on this information and feedback here, you can naively evaluate, assuming a single molecule gas, that the work that you extract or the heat that you extract from the bath is equal to kBT logarithm of 2, which is the famous result. So what we can do this in our circuit. So what we do is I now depict this single electron box as this two-level system here. So initially you put the system into this degeneracy point where the two charge states n equals to 0 and n equal to 1 are degenerate, and the particle can be on either side. Then you do a measurement. You use this SCT to measure the particle. If it's on the left, you quickly you trap the particle to this left well, and then after that you quasi-statically you expand the system back, or move the system back to the degeneracy, and in doing so you decrease you increase the entropy in the charge system from 0 to kB logarithm of 2. And now indeed, depending on the system and the feedback and the measurement, you really can make these two alternative ideal, essentially identical feedback protocols, and in doing so, you in the full cycle you always extract this kBT logarithm of 2 from the bath, putting it to the charge state. So before showing the actual feedback experiment, I show here what is the heat that we really produce in such a process. So this is kind of a deterministic experiment. So you start again with one well preferred, and you move the system towards the degeneracy. So if you do it many times and you evaluate how much heat you inject to the bath by counting the electrons that jump between the two wells, you see that if you do it relatively fast, you only and you come to the degeneracy, you extract a little bit of heat from the bath. So there's a negative heat production on the system. But then when you do it slower and slower, you find out that when you move the system from this sure charge state to the degeneracy, you have extracted about kBt logarithm of 2 of heat from the bath. Now, if you don't have any feedback and you continue deterministically to the other extreme, or you would come back, what happens is that you re-deliver this same heat or even more back to the bath, and the second law is nicely, of course, rescued in the sense. So, but the important thing is that what you do is you really, when you come from this charge state to the degeneracy, at this point you have to make a decision to know if the system is on the left or right well. So this part of this kind of deterministic protocol is, especially this right-hand side here, is quite well related to what is known as the Landauer principle. So you can erase a single bit, and this costs you energy of kBt logarithm of 2 at the minimum. This was done with a colloidal particle in the experiment by Sergio Siliberto in 2012, where they had also a two-level system where the particle is either on the left or right, well, undetermined initially, and then you modify the potential so that finally the particle is definitely in one of the wells. In doing so, when you do this slowly, you eventually find out that you are dissipating energy or dissipating heat which is equal to kBt logarithm of 2. So this is what we are doing in this second half of our cycle in this experiment. But now going to the actual feedback experiment. So here is again our single electron box where we do the whole protocol which I showed you a few slides back. So initially the system is in the degeneracy gate is positioned so that the electron is on the right or on the left, and at certain moment you do the measurement and decision. You find, based on the measurement of these charge states with the single electron transistor, you find that the system is now in a state where there are no electrons on the right side. After that, you move the gate to a position which keeps this charge state neutral, and then you start to move the gate slowly back to the initial position. In the beginning, you naturally don't see much transitions because this charge state is preferred, but when you come closer and closer to degeneracy, you start to see transitions between the states n equal to 0 and n equal to 1. And then when you come back to this position, you again make a measurement, and now again, depending on in which charge state you find the system, you move the gate either down or up accordingly. And in each of these cycles, you can again evaluate how much heat you have dissipated to the bath just by registering this gate voltage and counting over all these transitions. And this is the histogram that we obtain in this case. So this is here what we have is work divided by kBt, but since it's a cyclic process in the long, if you make a lot of repetitions, there is no difference whether you talk about heat or work. And then on here we have the histogram, so we collected maybe about 3,000 of such cycles, and what you see is that the work has a negative average for these events in particular, and it is centered very close to minus kBt logarithm of 2. There are, however, there are events where the work is highly positive, and this positive work is because there are, as you see, the detector is not perfect. You can make an error because of the noise of the detector, and if you make an error, there's a big penalty of energy because the system is in the excited state when you drive and it relaxes back. So when you average over all this histogram here, you find out that on the average, you have extracted about 75% of kBt logarithm of 2. One can do a little bit better, and you can find that if you include really the mutual information of the measurement, which depends on how good is your measurement. So the mutual information in this two-state system is given by the error probability in your measurement. So if you have a possibility of making an error in the measurement due to the noise of the detector, then it gives you a based on these conditional probabilities of measuring state n when it's m and so on, you can find out what this mutual information, what values it has. And in the experiment, what we can do is we can tune this or we can vary this error probability by changing the bandwidth of the detector, which means that the detector currents, these SCT currents, either they overlap heavily if there is a large error probability, or when you make it slower, in fact, then you can make them essentially separate. And by tuning this error probability, you can find that if you test this Sagawa-Ueda equation, you find that this fluctuation relation is valid within a few percent. Whereas if you would not take into account this mutual information, it has a value which, in fact, and ideally it approaches 2. Okay, so this was all kind of indirect measurements of work and heat. And what we were kind of thinking that there's also a possibility to realize a autonomous system. So in these systems, I told you that we were having here we were having a detector which is measured, is a single electron transistor, but the feedback is done by collecting the information back from the cryostat to the room temperature, and the computer gives you the feedback to change the gate voltages. But there's also a possibility to make something which is an autonomous thing, where you have a single electron circuit which is controlled by another single electron circuit directly. The advantages here are that in this case you can make the cycle much faster. In the earlier case we had like 1 Hertz level of operation. Now we can go up to several megahertz, which means that you can not only measure indirectly the heat, but you can also have heat extraction which is so large that you can measure it directly as changes of temperature on the system. Another advantage is that when you have a Maxwell's demon which is directly on your chip, you can also see what is the energetics on the demon itself. And the system that we realized was that we have a single electron transistor which is somewhat biased, chemically potential biased, and it has a very simple Hamiltonian because it has the charging energies of the two electronic systems here, and then a coupling Hamiltonian which tells you which is the Coulomb energy between the two dots in this system. So what you can create is that you can make a cycle where the system is autonomously running once it's set to its working position. So initially you have chemical potential difference between left and right here in the top part, but the dot itself has a higher chemical potential, so set by the gate, so that it takes some energy from the bath for a tunneling to occur onto the dot. And when this occurs, there's a Coulomb repulsion between the system and what we call a demon on the bottom here, and immediately the charge is escaping from the demon to the lead, from here to there. And at this moment, the potential on the island drops, and again the electron sees an uphill to tunnel out from the dot. And this goes cyclically here, and one can always at each transition here, if it works ideally, you extract heat from the bath, whereas in the demon itself, of course, there are dissipative transitions. And all this is mediated by the capacitive interaction, so Coulomb interaction between the two systems, given by this coupling term here, determined by the capacitances in the system. So what we do is we measure the temperatures in this system. Not only here is our single electron transistor, which is biased. Here we measure the temperature on the left lead, we measure the temperature on the right lead, and we measure the temperature of the Demon island also. And this is done by very standard tunnel junction thermometers, which can measure tiny changes of temperature. And at low temperatures, we work usually at 100 millikelvin or below. The coupling to the bath is very small, and also the heat capacitors are very small. So we can really measure the kind of the steady state temperature change when this system is running. So what we see is, this is a little bit complicated picture to look at, but we see kind of diagrams which depend on the different gate positions of the system. So don't pay too much attention to this. This is just how it looks like. And then this is what we predict, and here is the experiment. So now if we just measure, this is the current through the device. So now we measure the temperatures of the three positions, and what we see is that as a function of the gate position of this system here, we see that in the case when this demon is set inactive, and it can be set inactive by tuning it off from the charge degeneracy point, so that now no transitions occur in the demon. What happens is that there is at some gate positions we can see that the left island is cooling because the transitions are occurring here uphill. But at the same time, in the other side, the electron tunnels downhill here, and it produces much more heat. So this is shown, for example, by this blue curve here. So you can see that well, this is shown by the temperature of the left lead here. At this position is cooling because we are at this position here, but the right lead is heated because there's heat deposited to the right electrodes. And there's a similar position on the symmetrically when we are in this position here. But overall, there's always a heat dissipation in the system. But then the demon itself, which is down there, its temperature stays essentially constant all the time. But when you go to the position where these two talk to each other capacitively strongly, then what happens is that you can have a gate position where both the left lead and the right lead are cooling simultaneously. At that time, the demon itself, capacitively or Coulomb reacting to the top part, is getting heated. So this is where we have kind of autonomous Maxwell's demon operation. So we can cool the whole system on the top due to this interaction between, or this mutual information, in fact, between the two parts of the system. So this much. How much time do I have now? Do I have only 5 minutes? It's a pity. So okay, so now this was kind of more or less classical all. So now what we are working, I told that this was kind of an effort of about 5 years up to now, but now we are working on really quantum systems. So our two goals are to to really measure kind of stochastic thermodynamics in a quantum system by driving the system and measuring the environment. And measuring the environment means that we realize small baths which we measure by single photon detectors. Another part which I think I have time to briefly describe is our heat engines here. So what we are doing is that we have superconducting qubits which are made in-house, and they are kind of these days standard transmon type qubits where the coherence times without these mini baths, so when they are not loaded by some dissipative baths, are of the order of several microseconds, so they are good for our studies. So the idea here is that you would drive a qubit and you would then couple it through the cavity to this mini bath, which is in our case a metallic absorber, and you see its temperature as I described earlier, but now due to the transitions in a quantum system. So it allows you, in principle, to monitor the full quantum jump trajectories of the system. And in order to do this, I just show you here some estimates because we are still working on it. So in principle, in these detectors, they work at temperature of about 100 millikelvin. They are small metallic resistors whose heat capacity is expected to be about 10 to 3 kb at the low temperatures. In fact, we have seen some excess heat capacity in the recent measurement, and this is the main showstopper at the moment to reach this single photon detection. Nevertheless, if we think about quanta which are of the order of 1 Kelvin, then we expect that these temperatures change by about 1 to 3 millikelvin upon the absorption of the photon. And then the system relaxes back to the bath at the time constant, which is of the order of tens of microseconds. So in principle, we already, if the heat capacity would be what we expect from the simple Landau Fermi liquid linear in T, then we would already have the resolution for single photon detection. But this is not at the moment quite the case. So we are about 1 order of magnitude off from this. The thermometry that we do is we do fast thermometry on tunnel junctions, so we can really measure the temperature of these conductors on the timescales which are of the order of 0.1 microsecond. So if you allow, I would tell 5 minutes about this heat switch and refrigerator. So what we are now working at the moment is to really use a qubit as an element in a quantum refrigerator or as a heat switch. So the idea is that you have 2 of these mini baths, and then you control, for example, by magnetic flux, the coupling between the 2 baths, and you can do this either in a static way or you do it in a time domain, changing in time domain, and you can even pump the heat from cold to hot. So the idea of the refrigerator is shown here. It is a qubit which can be a transmon qubit, a flux qubit, and its level spacing between these 2 levels is varied by this magnetic flux. Then it is coupled by mutual inductance or by capacitance to 2 cavities or 2 LC resonators which embed a bath made out of these resistors. So now if these 2 resonators have unequal LC resonance frequencies, then what one can do is you can make a 4-stroke engine out of this, or 4-stroke refrigerator, in fact, where, say, initially the system is such that this is biased to the point where the level spacing is at minimal here, and then we assume that it is in resonance with the cold bath here. Then the population in the qubit is determined by this cold bath here, and after that you change the flux position, and the 2 systems decouple from each other. And this is kind of adiabatic phase where the population remains constant until you increase this level spacing such that it resonates with the left reservoir here. And in this case, the system relaxes essentially back to the ground state. Again, you move the flux such that the system is fully decoupled from the 2 baths, and it stays in the ground state as long as it hits again the resonance with the right one, and then the population comes back. So in this process, the heat is transferred from the cold bath to the qubit and then to the hot bath. And this can be realized by just making a sinusoidal drive of the flux between these 2 extreme values shown here. So what is interesting here is that despite the fact that in fact it seems to be so that you can't really beat what you would obtain by the classical rate equation analysis of a 2-level system. What you see anyways is that when you do this as a function of frequency, you see that the power that you deposit to the cold bath, this means, since it's negative, it means it's cooling, is initially is essentially it's linear in frequency, because you have this well understood expression where you assume that there are fully adiabatic and fully thermalized phases in your cycle, and then it should increase linearly. But when you start to drive faster and faster, what happens is that the system starts to have like Landau-Zener type dynamics, and the off-diagonal elements also matter in the heat transport. And you see kind of repeated oscillations of the heat as a function of frequency corresponding to these excitations. So up to now, we have not yet seen this or done this experiment, but what we have done is we have used a qubit as a heat switch. So assume that you have two of these resonators, and then you change the flux through this qubit, and these two resonators are nominally identical. In this case, at a certain moment or at certain value of the flux, this system is coupled to both of these two baths simultaneously. And you can expect that there is heat that is transported through this qubit resonantly. And this is indeed what we have seen. So we have realized a system where we have two baths. Here is the hot bath, here is the cold bath. We change the temperature of this bath, and we measure how much heat is absorbed on the other end here. And we do it as a function of this magnetic flux. So what we see in this experiment is that indeed there is a change of temperature in here, which corresponds to how much is the heat flux coming from the hot bath here, and it's modulated by the magnetic flux. And we have these resonances always when the qubit frequency is equals the LC oscillator frequency repeatedly. In some other experiments, we have seen much less trivial behavior, and I just want to very quickly show what is the origin. So this comes essentially from this simple model which I showed here, assuming that these two oscillators are as classical environments to the qubit, and then we are expecting to see this behavior, but this behavior is somewhat less trivial to obtain. So in this first sample, indeed, we can assume that we have like qubit which is coupled weakly to this resonant environment here, and then this is what produces this behavior that we see in the experiment. So this is kind of a resonant environment model. So there's kind of a quantum classical cut or Heisenberg cut, which is between the qubit and the resonator. But then in the other experiment, what we had to invoke is that we assume that the two resonators and the squid of the qubit form like essentially three harmonic oscillator system, which is weakly coupled to two of these baths here. So it's like a James-Cummings-like model for this qubit, and it works when this coupling here times the quality factor of the qubit is larger than 1. And doing this consistently, we find, I don't have time to show the details. I just can show you that it produces this energy level diagram where you have in this four-state system you have this avoided level crossing when you tune the magnetic flux of the qubit, and at the end what we find out is that this experimental data can in fact be reproduced quite nicely by this model. So it's in fact it's an interesting crossover of where is really the quantum to classical cutoff when looking at the heat transported through the two. So I summarize here. So I have shown how single electron circuits with mesoscopic baths form quite nearly ideal platforms for stochastic thermodynamics experiments, and we have demonstrated the non-equilibrium fluctuation relations. We have realized two different types of Maxwell's demons, and at the moment we are working on this, I would say, truly quantum thermodynamics experience. Thank you.
Wonderful measurements. Congratulations.
Thanks.
Actually, I'm interested in the specific quantum features of
Yes.
these processes. And you have with your qubit basically all the means and all the technology in hand to measure the states which are
Yes.
happening at this region 2.
Yes.
So what kind of non-classical states do you
So,
expect?
Okay, so in fact, this is, in this case, what we have is just, how we model this is just 3 harmonic oscillators. And you can, and we assume that you can describe it in the basis of 4 basis states where you notate them by the state of the excitation in resonator squid and the resonator 2. And we could do this in this simple way because in our experiment the temperature is still, the temperatures, even the hot and cold path temperatures are much lower than the resonator separation. So then this very simple model seems to work, and we get, I don't show here what these states are, but they are anyways, they are superpositions of these 4 basis states in general. And this produces this energy level diagram and also this non-trivial heat transfer.
I have a question which is maybe illustrated by your title slide. So in this Maxwell-Demon picture that you had, there is a very heavy door that the demon would have to open and close. So it would require a lot of energy and it would be irreversible. Of course, that was just an illustration, but now I was wondering, in your first CLR engine experiment, actually this one, the mechanism is still classically changing potential. So I guess it really correspond to having a heavy door.
Yeah.
Interesting. This is actually my question. In your Maxwell-Demon experiment that you have later, where you have just actually both these things are qubits, it seems that you have in some way resolved that because now the control is also just a very small system.
That's right.
So is it correct to say that this would really implement so the mechanism of the door, so to speak, would no longer require any extra energy?
Yeah, so I think we can essentially measure all that because we have the handle of measuring all the dissipation at each point of the system.
So if you measure it, would the operation of the door itself cost energy? Because one would ideally want that the amount of energy that is wasted to operate the door is smaller than what you
Yeah, of course. So
is this the case?
I think it's the case, but I mean, in the first demon experiment, we had no control about how much energy we put. I mean, for sure, in reality, to control the computer, everything, we put like billions and billions of more energy there. But in this case, we don't do anything. We just put a DC bias on, and we measure how the system evolves. Nothing. So I think in this case, the opening and closing are not requesting it. Maybe.
Okay, to hit up a little bit the bite, maybe you can show this nice picture with Maxwell-Demon. This. No, this was the first.
Yeah.
Oh, okay. Okay, so it's enough to make a hole here and put the string down, and you see that you do not need any information about the position of the molecule. It will work on both sides. So there is no really connection between information and thermodynamics, at least in this case. The whole work is performed by this partition. Partition divides them into parts and compresses gas. So the work is done in the very beginning. It's much higher even than KT. It's must be larger than KT. So this is the initial mistake of Stiller, which developed to this whole big theory. So I would like to warn only about this.
One more question. If you treat the squids classical, can you test in this last model, in the last system that you showed, can you test the fluctuation quality?
Fluctuation relations in this case. Okay, so in order to really do fluctuation relation measurements in this case, we would need the single quantum level detector, because this is what we do here is we are measuring just the average power transmitted. So we have no tool yet to measure the stochasticity or say the fluctuations there. Or of course, we can see some fluctuations. We can see some fluctuations of heat current, but not on the level of a single event yet.
So you have shown that you can use your system for cooling.
Yes.
Like I think you
Yeah.
showed the scale of like a millikelvin or something like this.
Yeah.
I was just wondering, what's the temperature of the device at this point?
It's about 50 millikelvin. 50, so it's like few percent cooling. Yeah.
Okay.
And here also we could, by the way, we can cool the system by a few millikelvin.
You have a question? I don't. I don't know what to do with Robert's statement. We could argue forever, but should I just leave it or?
About the Szilard engine.
Start it, you can't leave it with us. Here's the last question before coffee.
Yeah.
Robert wants to put the piston in the middle and let it be pushed out to either side, regardless of what side of the piston the molecule is on.
Yeah.
But if he does that, then he's creating an extra bit of entropy in the box. So, of course, everything balances. If you draw one bit of work, then he's creating one bit of entropy into the box. So that's the trade-off. So you still have information, you're still extracting work from information, but in your particular case, you're adding in information and therefore extracting.
Okay, I disagree.
Well, this is what we see in the identical setup.
Okay, let's thank you.